Okay, so 5.2 is on series. Okay. If we take the terms of a sequence and we add them together, we get something called a series. A sub 1 plus A sub 2 plus A sub 3 plus ... forever is called an infinite series. And is expressed as this symbol, capital sigma, it's a Greek letter sigma, stands for sum. Okay, sigma sum as n equals 1 to infinity of A sub n. So now we're going to add up our terms, okay, as an infinite series. Okay, for example, if I take the series n equals 1 to infinity of 1 over 2 to the nth, okay, that equals 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and goes on forever. Okay, we could talk about something called a partial sum of the series. So our partial sums, okay, are what everything is added, the sum, all of the terms up to a certain term. So these are our kind of subsums. So the sum of just the first term here is itself, it's 1/2, okay, or A sub 1. Okay, the sum of the first two terms would be 1/2 plus 1/4, which would be 3/4. Okay, the sum of the first three terms would be 1/2 plus 1/4 plus 1/8, which would be, what would that be? That's 6/8 plus an eighth, which is 7/8. Okay, and we could talk about the partial sums here. Okay, definition. Given a series, the summation as n equals 1 to infinity of A sub n equals A1 plus A2 plus A3 plus ... Let S sub n denote its nth partial sum. Okay. That is, S sub n is equal to A1 plus A2 plus A3 plus ... all the way up to the nth term. This is equal to the summation as I equals 1 to n of A sub I. Okay. And we say that S sub 1, S sub 2, S sub 3, S sub 4, all the way to S sub n is the sequence S sub n if the limit as n goes to infinity of the partial sums, the sequence of partial sums, okay, is equal to some value, some limit S, it exists and is a real number then the series the sum as n equals 1 to infinity is convergent and its sum is S. Okay, that is the sum n equals 1 to infinity of a sub n is equal to S. Okay, so we're taking our terms and we're saying, okay, what is this getting closer and closer and closer to? When we add these up, okay, is it getting closer and closer and closer to a certain value? If I keep adding the next term, does it get closer to that value? And then, okay, or does it just keep increasing forever? Okay, but if it does get closer and closer and closer to a value, the limit does exist, then the series converges to that limit, and we call that limit S. Okay, otherwise, it is divergent. I'll say the series is divergent. Okay, the geometric series summation of a r to the n minus 1 as n equals 1 to infinity is equal to a plus ar plus ar squared plus ar cubed plus dot dot dot. Okay, this has a partial sum S sub n equal to a times 1 minus r to the nth power all over 1 minus r. And if the absolute value of r is less than 1, it means it's a fraction. It's a number between -1 and 1. Okay, then the sum S, the limit of this sum, is equal to the first term, a sub 1, okay, divided by 1 minus r. Thus, it is convergent to S IFF, that means if and only if and only if r, the absolute value of r is less than 1. Okay, otherwise, it is divergent. Okay, so this is called the geometric series test. Okay, and R in this case is called the radius of convergence. Is it called the radius? No, what is it? No, I don't want to go there yet. R is what is it? It's the common multiple. What is it called?
Ratio.
No, it's a common, what is it? It's common factor, I think. Let me see. I don't know why I'm blanking this term. Um, okay, consider the geometric series. Common ratio, that's what it is. Again, I don't know why I had ratio in there, is the common ratio. I had ratio of convergence, but I didn't want, I knew it was wrong. Okay, common ratio. Okay, R is called the common ratio. Okay, it's what we keep multiplying by to go from one term to the next term. Okay, common ratio. Okay. We can test the series to see if it is convergent or divergent by the geometric series test, and then find out, well, what does this thing converge to? Okay. Okay, let's look at an example here. Number one, is the series the summation as n equals 1 to infinity of 2 to the 2n, 3 to the 1 minus n, is this convergent or divergent? Okay, so is that convergent or is it divergent? Okay, so this is n equals 1 to infinity. Okay, I'm going to rewrite this a little bit so I can get it into something that has a common ratio. I'm going to rewrite this as 2 to the 2 to the nth power times 3 to the first times 3 to the negative nth power. Okay. This is going to be equal to n equals 1 to infinity of, this is 4 to the nth power times 3 times 3 to the negative nth power. Okay. So this is going to be equal to n equals 1 to infinity of 4 to the nth. I'm going to pull that 3 out in front, one of the 3's out in front. Let's pull one of those 3's out in front. I get 4 to the nth times, this is 3 to the negative nth power. That's 1 over 3 to the nth. So this is going to be equal to the n equals 1 to infinity of 3 times, I'm going to put this 4 to the nth over 3 to the nth. And now I can rewrite this as n equals 1 to infinity of 3 times 4/3 to the nth. So this is geometric with a common ratio r equals 4/3, but that's greater than 1. And so what do we say that happens if r is bigger than 1? If r is bigger than 1, then what happens to the geometric series? Well, if it's bigger than 1, then it diverges. Okay. Therefore, the series diverges. Okay, number 2. Okay, find the sum of the series summation as n equals 0 okay, n equals 0 to infinity of x to the nth power. Okay. Okay, so what does this look like? N equals 0 to infinity of x to the nth power. That's going to be x to the 0 plus x to the first plus x squared plus x cubed plus dot 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 dot. This is equal to 1 plus x squared plus x cubed plus dot 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 dot. Now if x is greater than 0, this thing diverges. It's just going to continue to increase. I'm going to continue to add bigger and bigger numbers. So this diverges if x is greater than 1. Okay, but okay, and but this converges to a1 over 1 minus the common ratio, which is x in this case, or a1 over 1 minus r. Common ratio is okay, the first term a1 is 1, so this is 1 over 1 minus. My common ratio, the thing that I keep multiplying by, is x, okay? But this converges to this guy here, 1 over 1 minus x, if r, no, if x, the absolute value of x is less than 1. Mhm. Okay.
So it's always gonna converge to that Like no matter the problem, it's always going to converge to the a the 1 over 1 minus r if you can prove it's converging.
If the value of x is between -1 and 1,
Oh, okay.
then it will converge to this. If it's bigger than 1, then it won't. Okay. And then if it's less than 1, well, we haven't really dealt with that yet, because that's what we call an alternating series. And we'll deal with that a little bit later. But this just helps us to set things up for a geometric series. Okay. Let's see if we can move on to the next one. Okay, number 3. Okay, find the sum of the summation as n equals 1 to infinity of 1 over n plus times n plus 1. Okay, in this case, we're going to have to change this to a partial fraction. Okay. So multiplying through, we get 1 is equal to a times n plus 1 plus b times n. So 1 is equal to an plus a plus bn. This tells me that a must equal 1 and a plus b must equal 0. Okay, if a is 1 and a plus b must equal 0, then b must be equal to -1. So this is really the summation of a, which is over n, which is 1 over n, minus 1 over n plus 1, as n equals 1 to infinity. And this has a really nice property. It's called the telescoping series, in that every other term cancels each other off. So when we write this out, we're going to write out the terms. I'm going to plug in 1 here. That's going to be 1 over 1 minus 1 over 2, plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, plus this goes forever. Okay, this is plus 1 over n minus 1 over n plus 1 plus dot dot dot. Every term except for the first term. Okay, and the last term will cancel out. So we would say that this is equal to 1 plus the limit as n goes to infinity of 1 over n plus 1. But that thing's going to go to 0. And so the limit is just 1. Okay, the summation of this is just 1. It's the first term. Everything else cancels out. And this is called a telescoping series. Okay, so it kind of like folds in on itself, kind of like the spyglasses of yesteryear. Okay, let's do one last example here. Okay, number 4. Okay, show that the harmonic series okay, oops, summation 1 over n as n equals 1 to infinity, okay, is divergent. Okay. So show that this thing is divergent. Okay, that it keeps, we keep adding more and more values. Okay. So if we take some partial sums here, like s sub 2, that's going to be 1 over 1 plus 1 over 2, which is 1 and 1/2. Okay. If we take s sub 4, the first 4 terms, that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. I'm going to say that this thing is greater than if I took the following terms. If I took the term 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 4. Because what this is going to be equal to is this is going to be equal to 1 plus 1/2 plus 1/2. This thing here becomes a 1/2. So this is 1 plus 1/2 plus 1/2, which is 1 plus 2 over 2. Okay. If I take s sub 8, the first 8 terms, you get 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. When I look at these last 4 terms, I could say that this is greater than 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 4 plus, and then we're going to have 4 of these, 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. You see how each of these terms is 1/8? And 1/5 is certainly bigger than 1/8, and 1/6 is certainly bigger than 1/8, and 1/7 is certainly bigger than 1/8. So if I only add up 1/8, okay, I should get the partial sum s of 8 should be bigger than that. Okay, but this thing, when I add it up, this thing becomes, okay, 1 plus, so this is a half, 1/2, and then this is another half, because it's 4/8. So I get 1 plus 1/2 plus 1/2 plus 1/2, that's 3 halves. And we could keep doing this forever, and we would keep adding more and more and more more numbers. If we said the sum of s to the 2 to the nth power, okay, is greater than or equal to 1 plus n over 2. Okay, so 2 to the first power was 1 plus 1/2. Okay, 2 to the second power was 1 plus 2 over 2. It's greater than that. So if I let n go to infinity, this thing just goes off to infinity, and so the thing is divergent. Okay, it just keeps bigger and bigger. Okay, therefore, as n tends toward infinity, s sub 2 to the n also tends toward infinity. And so my original s sub n is divergent. Therefore, the harmonic series, we call this a special series called the harmonic series, summation n equals 1 to infinity of 1 over n, is divergent. Okay, the partial sums are not going to 0 fast enough. Okay, we keep adding more and more numbers. Okay, so if we look at a graph, okay, of what's happening with the harmonic series, okay, the terms do not go to zero fast enough. And so I keep adding more and more and more values. Okay, and those values accumulate. Okay. Does not, we look at, this is a sub n is equal to 1 over n, does not go to 0 fast enough. And so the graph of the partial sums keeps going up. So if I'm at s sub 2, s sub 4, way over here at s sub 8, okay, I was at 1 and 1/2. Maybe we'll do 1 and 1/2 there. I was at 1 and 1/2, and then I was at 1 and 2/2, which is 2. And then I was at 1 and 3/2, which is here. And so we keep going up. Okay, it just keeps going up and up and up. It goes up slowly, but it keeps going up and up and up forever. As I go out twice as far, I go up the same amount. Go up twice as far, go up the same amount. Go up twice as far, go. So this thing tends toward infinity. Okay, theorem. If the series summation of a sub n equals 1 to infinity of a sub n is convergent, meaning that it converges to some value, then the limit as n goes to infinity of a sub n must have been 0. Okay, then the sequence had to have gone to 0. It means the terms had to have gotten smaller and smaller. The terms get bigger and bigger, then this thing is going to diverge. Okay, because you're just going to keep adding bigger and bigger numbers. But if it was convergent, then we know the terms had to go to 0. The opposite is not true. Okay. So this is one way only. Okay. This is incredibly important because a lot of students will get this wrong. Okay, this only works in one direction. Okay, so if the series is convergent, then we know something about the individual terms. They have to be getting smaller. However, if the terms are getting smaller, it could be divergent. The counterexample is the harmonic series that we just did. The terms are getting smaller. The limit, okay, of 1 over n gets smaller, but it doesn't get small enough fast enough. Okay, so this is one way only. So if it's convergent, then the limit as n goes to infinity of the individual terms goes to 0. Okay. This is not a test for convergence. Okay, you cannot use this as a test for convergence. Okay, the harmonic series is a good counterexample. Okay, just because the limit as n goes to infinity of a sub n is equal to 0, that does not mean that the series converges. Because it just could not be going to 0 fast enough. Okay, it does not imply that it converges. Okay. Okay, next time we will talk about how we can prove that something diverges. Okay, but that is section 5.2.